I will talk about an algorithm that difficulties that arose when people try to run the same algorithm. And then I will discuss, as another point of reference, I will discuss calculations with small crossing nodes. Then I'll restrict to alternating ones, where there's two particular things I want to focus on, that you can obtain the oriented genus directly from an alternating diagram using classical Seifert's algorithm. And the other one is that you can calculate the genus of an alternating node from the Alexander polynomial. And then I'll, for non-orientable nodes, I will talk about work that allows you to determine the genus, the non-oriented genus of alternating nodes diagrammatically, starting from the diagram and building surfaces. And finally, I'll say a little bit about the what information you can get estimating the genus for alternating nodes from the Jones polynomial. All right. Okay, nodes span surfaces, and they span both orientable and non-orientable surfaces. As a matter of fact, if I give you an orientable one, you can always obtain a non-orientable one by adding a half-twisted band to the boundary, right? So the non-orientable genus defined here, I'm going to be looking for the smallest genus over all non-orientable surfaces, and is defined that way: 2 minus the Euler characteristic minus the number of components for a link. And even though the orientable genus has been studied practically forever, so a lot is known about it, the non-orientable genus got introduced later. People paid attention to it much later. So in particular, Clark in 1978 made the first preliminary observations about this. All right? And so, okay, by convention, for the unknown, people take it to be 0. But one thing you can note right away by doing the procedure I just said: if you give me an oriented surface, then I can put a crosscap, a half-twisted band to get a non-oriented one. If you do that in a smallest genus, then you have an inequality, right? You get a relation between an upper bound of the crosscap number in terms of the oriented genus. Another thing that's known is that for 2p torus nodes, okay, the genus, the crosscap number is 1. You've got yourself a Mobius band that you build out of the projection of a standard 2p torus node. And Hitoshi Murakami and Yasuhara gave an upper bound of the crosscap number in terms of the crossing number. So it's the floor function of half the crossing number. And they found that this bound is sharp often. And people have studied families of nodes. For instance, it is known how to calculate the non-oriented genus of several families: 2-bridge nodes, pretzel nodes, and many other families, several other families that I might be forgetting now. All right? But okay. However, for instance, when we started looking at this, we learned, before I didn't know that, a lot of the values in the node table, most of them I would say, right, are not known. And at least when I say there is no algorithm, at least the algorithm with normal surface theory that people have been known for calculating the oriented genus, orientable genus, has some sticky points here. Okay, so one issue too is that the surface that realizes the smallest, the non-oriented genus, does not need to be essential, right? So essential, these are non-oriented surfaces. I will say pi1 injective, and you can think of this as the double the surface and take the oriented double. Okay, so for instance, there are cases that to obtain the minimum non-oriented genus surface of a knot, the only way to do that is to stabilize, to do this crosscap stabilization in a oriented one. And so in all of these cases, you do see this local picture when you put the standard Mobius band, and this red sign, this red circle is going to give you a partial compression arc when you think of the orientable double. All right. And so this makes things difficult. And in fact, back in Murasugi and Yashuhara, for instance, proved that for the knot 7-4 of the knot table, this situation happens. So you are not going to find a maximal Euler characteristic non-oriented surface. All right. Well, by now things. Well, in fact, I just saw a paper by Nathan Darfield the other day where he shows an example of a knot where you don't even have any essential non-oriented surfaces, let alone maximal Euler characteristics. So, in particular, when you try to determine the cross-cap number, you have to solve those issues. Does this knot have essential non-oriented surfaces, and so on? Okay. So, for the orientable genus, in particular, there is an algorithm that will give you the genus of any knot, and the computational complexity of this has been studied by people, by Haas and Logarius, Peipinger, and so a starting point there, at least, is that the theorem of the classical process of Hackett's algorithm will give you that if there is any triangulation of the knot complement, and by the way, earlier I talked about Jessica talked about polyhedral decompositions, and for some point I will talk polyhedral decompositions and normal surfaces, but right now this is a triangulation in tetrahedra. So and you study normal surfaces with respect to these triangulations, and so then there is a way to add surfaces, and so if you cannot decompose it as a sum, this is fundamental. And so a starting point for these algorithms is that if there is a for any triangulation, there is a fundamental normal orientable spanning surfaces that realizes GK, the genus, the oriented genus of K. And so at least one can build an algorithm where one starts with obtains a suitable, and I don't want to say what suitable is, it's many things about triangulations, and triangulation of the complement. Then you go on to enumerate normal surfaces, identify the spanning orientable surfaces, and then choose the smallest one, all right? And okay, I mean, easy or not, at least there is a process that will give you one answer, a number, if you can get it to calculate, all right. So what about CK? So Ben Barton and Barton Orsland studied this problem, to what extent this normal surface argument can produce a single answer. And so what they found, I mean, the first the sticky point is that, first of all, you don't know that there is a normal surface even that realizes CK, and then you don't know that there is a fundamental. So just trying to make it normal will say that either there is a normal surface that will realize CK for me, or CK is twice the genus plus 1, and you're building your non-orientable surfaces in the fake way where you stabilize the Seifert surfaces. And then when you try to make it fundamental, an extra complication arises. And so the best that Barton and Osland could do is to say, well, here is an algorithm, and if it spits out one number, then this is your non-oriented genus. If it spits out two numbers, these are your choices. Okay? Okay.
Excuse me, but intuitively, we expect that surface with those properties exists, right? Like not a theorem, but like intuitively, do we expect that there's a fundamental non-orientable spanning surface in each case or not?
Do I accept that there is a no, non-orientable?
In case that C of k is one of those numbers?
Well, in this case, you don't have a non-orientable normal fundamental surface. All right? So there's an abstraction, yes. And the one abstraction is this trivial crosscap that I gave. So all right? So if it's not boundary incompressible, then you try to normalize it and maintain the Euler characteristic. And when you get there, you find that to normalize, you need to change the. All right.
I think in a particular triangulation, you might get lucky, even though you're not guaranteed to have this thing appear. It might.
Well, particular, but yeah, we're talking.
You have a very fine triangulation, basically.
Right. Yeah, Nathan has a point. I got a theorem that says, give me any, I can do this and this. Now, if you, sometimes you, yeah. Right. All right, so that's the idea. But nevertheless, Barton and Osland ran various algorithms. They made a lot of progress, and in particular, so one thing they did was to find upper bounds that were better than what was known before by error and trial, by trial and error. And then in many cases, they were able to go further and calculate several examples, actually, several low crossing nodes, up to 10, 12 crossings. So, okay. So now here is the point where I asked Jack Livingston for permission to copy not info. Okay, so what is known is, okay, this, besides the two p torus nodes that I mentioned, the cases of among the nodes of up to 12 crossings, the two bridge cases were calculated by Terracotta Hirasawa. The 7-4 was calculated by Murakami and Yoshihara. And typically, the node info is going to give you two numbers, an upper bound and a lower bound, right? Mostly an upper bound, though, because the lower bound for most cases was just bigger than 1. All right. And then Barton and Osland used normal surface theory and integer programming and so on, and they obtained, I don't have a number here, but several. And then Adams and Kindred, they gave a method to calculate the crosscap number of an alternating node starting from an alternating projection. They were also able to fill all the alternating ones up to, that were missing, up to 9 crossings. And then Christine Lee and I used our bounds to also improve many of these lower bounds previously known, and when we could, we got the answer. Okay, so the I want to talk about, I already mentioned state surfaces, and so I want to talk about state surfaces because this is how you find the oriented genus of alternating links, and this is how you find the non-oriented according to Kinder and Adams. And so the usual, so you start with a link projection, and there is a link diagram, and for any crossing there is two ways to split it. For this particular talk I'm not going to make a fuss to name the ways and make conventions, so there's two ways to split it. And so if I start with a node with n crossings, I've got 2 to the n ways to get rid of my crossings, combining this. And for each of those I can build a surface, all right? And the way you do it is when you split, all right? Can I write someplace here? Probably not. Probably. It's okay? Okay, so when you split, what you end up with is a collection of disjoint embedded circles, which you can make them bound disks on the plane, push them apart above the plane, and then go back and add half-twisted bands where you had your crossings earlier. I mean, in the case of, okay, if I add an orientation on my node, okay, we go like this, then I can, there's one way to split following the orientation, and so in this case I'm having the oriented splitting in each case, and in this case I'm always building an oriented surface, all right, and this is the Wald, sorry, Seifert algorithm. With this gives you non-oriented choices, and so altogether you build 2 to the n surfaces. And okay, I said push the disks apart. I'm not claiming this is going to give me a unique surface every time if I start pushing different ways, but the things I'm interested in this talk is Euler characteristic and orientability or not, so that's fine. I'm not going to change. Okay. And so these surfaces, I mean, the process for the Seifert surface has been known forever, but these surfaces were considered first by Pshetinsky. He defined them, and then for a while nobody did anything with them, and then a few years back Makoto Ozawa gave criteria for them in terms of the node diagram for these surfaces to be pi1 injective, and then people realized that the geometric types, if you're working in a hyperbolic node complement, the geometric types can also be described from the diagram. So in particular, you don't get parabolic ones, you get geometrically finite surfaces. And another thing that we've been using in work with Futer and Purcell is to get information, Jones type invariants and node complement, all right, incompressible surfaces. So they served as a bridge. And so Adams and Kidron found other application of these surfaces, which is to determine the genus of the non-oriented genus of alternating nodes. All right, so and going back, so the in the case of alternating nodes, a result of Gabay and Murasugi says that if you start with an alternating projection, is that right?
Well, Murasugi was like 20 years earlier, and also
Crowell.
It was Crowell. Should read this to Crowell and Murasugi.
Crowell, I thought, did mostly the polynomial because he was did. Okay. So Crowell and Murasugi did one proof in the 60s, and then later on there's another proof. Am I right? Okay, bye. So the point is, if you start with an oriented alternating projection and you apply Seifert's algorithm, that will give you the minimum genus over all surfaces. All right. So And Adams and Kidron gave what can be thought as an analog of this. And it goes like this. So you start with an alternating knot diagram or link diagram. And what you do is you think of it as a 4-valent graph. And when you do that, the complement of the graph has regions, right? So which you can think of as polygons with vertices, the vertices of the graph. And so if you have, it goes like this. If you have bigons, which will be probably, or so you can have this kind of thing, monogon, or you can have a bigon, or you can have other things. Okay. And in this case, so if I want to choose to consider just state surfaces, all right, I have to consider 2 to the n altogether. So the algorithm will bypass some of them. So let's begin with a projection. If there is a 1 gon or a 2 gon, I will resolve so that the crossings are resolved so that the region that is the bigon is going to become a circle. So for instance, okay, so here, when I had this kind of thing, I'm going to be considering only this kind of resolution out of the 4 that I have potentially 2 to the 2, right? Yeah. And for the monogon, I'm just going to do this one that makes it a circle. Okay. And then Euler characteristic argument, the basic one. If there is no bigon and there is no monogon, you got to have a triangle. And in this case, I've got altogether 8 ways to resolve, but I'm only going to be concerned with the ones that I show here. Resolve so the region in between becomes a triangle, or resolve this the dual way, the opposite way. Okay? So all the other resolutions are going to be decreasing the Euler characteristic in ways you don't want. And so you repeat this process for all bigons, for all triangles, and so on. And in the end, you choose S that has maximal Euler characteristic. Okay, and the point is, once you do that for any projection, this surface is going to have overall maximal Euler characteristic over all spanning surfaces, not just the ones you obtain by projections. And then their theorem is that run the algorithm with any diagram, any alternating knot diagram. In the end, look at the list you get. If there is a non-orientable one, this is your crosscap number. If there isn't, all of them are orientable, then you know that this is, the answer is 2 GK plus 1, and GK is either of your candidates in the end of the algorithm, all right? And, right, it doesn't matter which alternating projection you choose, because as I remarked earlier, well, we know that different projections of the same alternating knot or link are related by flipping. And so one can sit down and show that the set of Euler characteristics and the information of orientable, non-orientable is preserved under flipping. Okay? All right, so this is how you find. Okay, a basic example here. I've taken the figure 8 knot, and I have a lot of bigons here, which become an issue later on. But I resolved number 1. And then in the second step, I've got many choices, 1, 2, 3 bigons. I've got to consider all of them. And one thing that's kind of amusing, and it comes in the proof, I don't know if I'll say anything, but is that, okay, in the end, you might have both orientable and non-orientable surfaces that have the same Euler characteristic, okay? So, okay. All right. And then another, the other result I wanted to mention is that for alternating nodes, another classical result is that you can obtain the genus from the Alexander polynomial, all right? So this is a knot invariant, and you're looking at the degree, and the maximum degree, the degree span, let's say, gives you twice the genus. Okay. So now let's go to the Jones polynomial, and so I'll start with a knot, right? This for the Jones polynomial. Now, when your knot is alternating, there isn't much you can say about what I call AK and A prime K. All right. So the way I've written it, okay, N is the highest degree, S is the lowest degree. The top and last coefficient are plus or minus 1. So then I look at the second layer, Bk and B prime K. And so what we said is that what we found is that there is a two-sided bound of the crosscap number in terms of this TK business, all right? And this is the, in contrast to the theorem I said earlier, this goes with the upper, the ceiling function, all right? Because it's a lower bound. Okay, so, what is interesting is that this bound is quite effective in getting you the crosscap number for some nodes. Questions so far? Okay. All right. So, for instance, let's do nodes. So I've gotten rid of the K, the number of components, and here is a list of all 12 crossing nodes where the upper bound was 3. Okay, it's all about 1 that I couldn't fit on the slide, it doesn't matter. Where the upper bound was 3, alternating 12 and 11 crossing nodes. And in all these cases, the lower and the upper bound come out exact, and so you actually determine the crosscap number. Okay, so one comment. I said you go back to the Jones polynomial here, but actually, if you are interested to just get this sum of absolute values, you don't need to calculate the whole Jones polynomial, all right? I mean, calculating the Jones polynomial is also computationally difficult, as we know. So what you do is you can do this from any alternating projection, right? What you do is you take the checkerboard graphs, all right, and you just look at the Euler characteristics. You reduce them first, so every time you've got a pair of edges between the same pair of vertices, you remove one, so you take the simple graph, and so this is enough to give you the bit of the Jones polynomial that you need. And then, but actually you can do also, if you are interested just in getting the this information of the diagram, you can do a little bit better. What you can do is, if your diagram is twist reduced, and remember that was defined, but okay, so basically you can't reduce the number of twist regions by transforming crossings across blobs like that. If you can't do that, then it's twist reduced, and if it is twist reduced, then the twist number of a twist reduced diagram will give you exactly the quantity that I call TK, capital TK, all right?
What's the twist number of the diagram?
Right, so you are, a twist region is something that looks exactly like that. You're looking at the string about, and then you are counting the number of twist regions, right? So, for instance, take the 3-string pretzel knot that has 3 twist regions.
Okay, so if you have a twist reduced diagram, it's just the number of crossings?
No. Yeah, if it's a twist reduce, it means you cannot reduce the number of twist regions by flipping anymore, all right? So if it's a twist reduced, means every time I see that kind of configuration, then I know that I have bigons either here or outside. So I can do it, right? Okay, and also if you do twist regions, right? I don't need to, a crossing counts as its own twist region if, okay? There you go. So this is one crossing. So this guy still has 3 twist regions. All right. Okay, so, all right. Okay, and this is the way that I need to view the particular bit of the Jones polynomial to get the relation that I stated using some of the techniques that Jessica talked about earlier. All right. But before I go into this, let's see sharpness. Here is some examples. I have, okay, this is the sum node anyway, 10, 1, 2, 3, where the upper bound is sharp. This is again a case of a node where you are not going to find the maximal Euler characteristic non-orientable spanning surface. Well, 1, 2, 3, 4, 5, yeah. And then the right example, so this, in this particular case, all my twist regions are, all right, crossings, okay? And so what I get is 10, 12. What I get is that the upper bound and the lower bound both give me 5, which is the crosscap number. All right? So in particular for nodes that look like that, there is no twist regions that have bigons. The estimate tends to do particularly well. I don't know why. All right, for log crossing nodes anyway.
Does this upper bound hold more generally for arbitrary knot diagrams?
Yeah, I think so. You don't need alternating. You don't need. That's easy to get, I think. Both the twist number and both the Murakami thing. Yes, I think so.
It's just related to the coefficients of Jones polynomial that you need alternating.
Yes. And in mania, yes. All right. So, yes, we already said the upper bound works for everything, and it's not particularly hard to get. So for the lower bound, what we want to do is we want to kind of start with an alternating projection and run the algorithm of Adams and Kindred carefully, so that what we will do, the first step is we end up with a surface that is the complement of an augmented link. Right now, typically, if I draw down a surface and then I augment, remember what happens, the extra components, right, if my surface looks like that, the extra components I put will pierce the surface, right? So what I want to do is keep track, so I end up with a surface from which I can calculate the crosscap number, and it is in the complement of an augmented link. And then, well, we want to make it normal and apply the combinatorial Gauss-Bonnet formula that Jessica mentioned, and get the estimate. All right? So how do I do that? Okay. So for instance, one thing I want to do is how will I augment these particular cases. So I see a twist region looking like so, and Adams and Kinder tell me resolve so that these bigons become circles, all right? And then when you build the ciphers, the state surface at this particular stage is at this particular piece will look like that. So you add your augmented link. When you're doing the triangles, you have to go augmented in a nice way, so that you end up with a something you can put in the complement of an augmented link. All right. So okay, here is again the knot and how I would augment, as Jessica said before. One starts with a knot projection and then they augment going backwards. So there, I picked one that has two twist regions, and I put the two red components. I untwisted the even number of twists, and I ended up with L. And then really, when I want to flatten it, I will remove that. But so we're using this polyhedral decomposition that Jessica mentioned, where you have two polyhedra, truncated vertices. Your dihedral angles are pi over 2, 90 degrees. And so you've got your boundary edges and you've got your boundary faces, which is where you truncate it. And these ones here are rectangles. Remember how it goes, and around your vertices you go like this. Okay. And you've got your checkerboard coloring. Okay. All right. So then I will take. All right. Okay. Now let's take a. I will take a surface that has realizes the crosscap number. Remember that is not incompressible in general. It is not boundary incompressible. All right, meaning the double. And so what I will do is. We will run the algorithm, the normalizing process, and there is two choices again, but you can calculate your crosscap number from the normal surface. All right. So the point is that as you normalize again, you may not retain the Euler characteristic, which is what you're interested in, but in the end you're able to somehow use it. Okay. And using the combinatorial area. All right. By the way, so here is some normal disks, and I'm using the recalling the formula here again that Jessica had, combinatorial area normal disks. M is the number of interior. Interior edges of the polygon, and the polyhedron. And by the way, the example that I have here is not an example that comes from augmented links, okay? It's just a random example I drawn. So when you were using this, don't try doing that, all right? You're gonna get 0 where it's not 0. It's just, I didn't pick my example well. These are triangles, and they should be all rectangles if I picked it out of a augmented link decomposition, all right? Okay, and so using the Gauss-Bonnet formula, one thing that comes out of the, I think, out of Leichenby's analysis, and in fact, I'm not doing admissible disks. So for normal disks, that should be known even to Casson. I don't know, probably, right? But anyhow, the combinatorial area is at least as big as the total length of the boundary. And then one thing, so once I have that, we're done, because one thing that Future and Parcell estimated is to just go around and analyze this combinatorial cusp geometry. And so, in fact, there is a formula that would give me the length, and a lower bound of the length in terms of the twist number. So that's something that I can just plug in, all right? So they tell you if you're looking at the length of a component that goes through T twist regions, then your length is pi times T times the number of crossings in each twist region it passes, and the smallest number of crossings. So once you have that, you're basically done, all right? And yeah, that's basically the idea. I wanted to say a word on non-alternating nodes, right? So any questions? All right.
So where does this twist number over 3 come from?
The twist number over 3 comes from. Is that directly from Futter? Yeah, pretty much, right. So it comes from the fact that LC gamma. So if gamma is a slope that goes through n twist regions, and tau is the number of crossings, least crossings in those twist regions, this is basically pi n tau over 3. Is it? Yeah. So I can, yeah. In fact, since, right. Let me actually write this down, because I need to use it. Right, so, yes, 2 pi n over 3. Right, and in fact, so, non-alternating nodes, right? So, you can say something for non-alternating nodes in general. In fact, okay, a lot of this goes through the non-alternating node. So you are not going to have your surface being in a complement of an augmented link. So when you take your surface now, okay. So let's say that I have a surface for K that realizes. I have to account that in general the surface would look complicated, but in general, if I augment, all right, the augmented components are going to pierce the surface, and so I have to view this as a surface with extra boundary components in the complement, all right? And so when I do that and plug in the what I'm trying to say is I will have this that comes directly, no pi this time, plus n tau over 3 minus n. Okay, where tau is the minimum number of twist regions my diagram has. So there is always some kind of estimate. I'm sorry, that's not equal by no means. All right, and so you can say something if you have tau being at least 6, all right, then you still get something meaningful here. So you still get the lower bound, right? So if I want to look at non-alternating knots, I can still say something using these techniques, provided that I will say that I'm looking at knots that are highly twisted, so they've got a diagram where each twist region has at least 6. I don't think I need 7, 6 will do it. And in fact, Jessica David used that to estimate the oriented genus, right? But with what I've got here, the calculation will go through just say a similar bound for the non-oriented genus. All right, so the bound I had earlier in terms of twist number, provided that my diagram is twist reduced and all, will work. And again, you can go on in this case to express it in terms of the Jones polynomial. The bound is not so good itself, and the fact that you're putting 6 crossings per twist region doesn't make it useful to make calculations with small crossing knots. So I haven't really said anything in this case. All right. All right. And I just want to finish with a question. So the question is, does the Jones polynomial determine the crosscap number of knots? Coarsely, is there a relation? I don't know at all. But the thing is that the great, I don't know this question, but the answer to what got it started is the Kovanov homology business, as I said. And one thing that we see so far is that when I'm talking about the Jones polynomial, really, in the end of the day, in these two families I looked is the twist number, right? But nevertheless, there is a reason to believe that the particular portion does much better than the twist number in estimating geometric things. And okay, so I'll just ask the question anyway. The Alexander polynomial gives me the the Alexander polynomial gives me the oriented genus of knots on the spot, the degree, and then it doesn't determine, of course, the genus of all knots, but what does determine is this much stronger, the refinement, the Higert-Floer homology. And so this question is looking in the non-oriented sense, is the Kovanov homology, which is a similar extension, a similar flavored extension, refinement of the Jones polynomial, determine the non-oriented genus. And I mean, there are some ideas around defining Kovanov homology in terms of surfaces to begin with, but so far there is no, I don't know, that's in progress, but that's what started anyway, our project. And as I said, we sidetracked and learned a little bit that wasn't known. So I think I'll stop here.